Good morning, ladies and gentlemen. It's a great pleasure being here today to present this talk online to the audience of ICWPT 2021. And first of all, I would like to thank the organizer of the conference for their very kind invitation. And although I'm not able to present this talk in person at the conference, and I hope that this presentation will generate some interest and will further generate discussions among the audience. And the topic of my presentation today is convenient viewpoints to higher order compensation in inductive power transfer converters. And I'll start with some background information, which is based on a workshop that I gave a few years ago, summarizing the theory, analysis, and design of second order compensation in IPT application. And here's the link for downloading the information for those of you who are interested. Now, the purpose of this talk is to try to connect second-order compensation with higher-order compensation in order to provide a systematic pathways or design pathways for designing higher-order compensation circuits to fulfill certain design and performance objectives. So naturally, our starting point will be the second-order compensation circuit. And in fact, in all IPT circuits, the transformer is usually having very weak coupling, and so a significant leakage will be present at the primary side and the secondary side of the transformer, and that transpires a mandatory need for compensation. And the purpose of compensation, obviously, is to try to eliminate the reactive power being circulated in the circuit and to try to improve the power transfer capability. And if we incorporate resistances in the model, we'll be able to identify the condition for optimal efficiency as well. Now, here's the simplified system model, and this transformer in the middle, and then we have the primary compensation circuit and the secondary compensation circuit. This is the inverter necessary for converting DC to AC, and then from AC to DC through the rectifier. So if we ignore the inverter and the rectifier for the moment, we focus on the compensation circuit, and we can identify 4 different types of compensation circuit depending on the input termination and the output termination. And namely, these compensations are series compensation, series parallel compensation, parallel series compensation, and parallel compensation. And note that for primary series compensation, the input terminal must be a voltage source. And for primary parallel compensation, the input terminal must be a current source. Now, we are actually able to generate a complete set of formulas and analytical equations characterizing the operating conditions. And in particular, I would like to draw your attention to 2 very important conditions. One is LIV, standing for load independent voltage, and also LIC, standing for load independent current. That is when the voltage is at the output is constant irrespective of the change of the load. And for LIC, that is a constant current irrespective of the change of the load. So here I have shown a particular circuit with input voltage termination, and A1, A3 are the primary and secondary compensation circuits respectively. And we can actually use this very general model to produce analytical equations that based on which we can analyze the circuit in detail. Now, I will just give you some key results, and so that we will be able to move on to extension to higher order compensation. And in this particular page, I'm showing you the LIV conditions. For example, the SS compensation circuit. Here we identify this point and this point where the voltage gain remains unchanged irrespective of the change of the load resistance. So for different load resistance, this point and this point basically overlap. In other words, the voltage gain constant, so that's the LIV conditions. However, for this SS condition, we realize that the efficiency is not optimized. Whereas for SP compensation, for this particular case, we have this point identified as the LIV condition, low independent voltage condition, at this particular operating point, and also the optimal efficiency point as well. Now, you would use G as the transfer function corresponding to the optimal efficiency point, and the H as the transfer function which correspond not to the optimal efficiency point. So in practice, usually there are two operating frequency, and the upper one is preferred because of the possibility of generating the zero voltage switching with slightly inductive input impedance. So in summary, we have the 4 different types of second order compensation. For the SS, the input must be a voltage, and the output could be voltage and current. In other words, the output could be LIV and LIC, but with LIC, we can actually get an optimal efficiency condition. So we have G function, H function corresponding to the transconductance and voltage gain respectively. And also for SP, for example, and for G it is the current voltage gain, and for H it is transconductance. And here in this case, the input is a voltage and the output could be LIV and LIC. And for LIV, we are able to identify the condition for optimal efficiency. So similar results can be obtained for the other two compensation circuits, PS circuits and the PP circuits. So the key point is that all these circuits can actually achieve LIC and LIV, but each circuit will actually have a preferred operating condition where the optimal efficiency can be obtained. Now, let us look at how this circuit could actually be extended to higher order. Now, first of all, on the input side, the input terminal side, we have to comply with the particular type of input termination. For example, SS and SP, the input must be voltage. For PS and PP, the input must be current. Now, if we are looking or focusing on the input terminal being a voltage, then the PS and PP, because this is fundamentally current, we could actually convert it to voltage by adding a inductor like the one shown here. Okay, so for the current source, we are able to actually convert it to a voltage behind an inductor. And for the PP case, again, we can actually replace the current source with a voltage source behind an inductor, so that it will become terminated by an input voltage source. Now, this is one extension, and our purpose here is to try to understand, by extending the input side with an inductor, whether it is producing any desirable performance or desirable feature. In fact, for PS, for example, extending to LCS, that is additional inductor connected behind this voltage source. So this is basically a PS circuit, but extended to a third order circuit. And in fact, we are able to generate the input impedance formula and also the input current, and from which we are able to identify the condition for the input voltage being the circuit being less sensitive to the input voltage variation. And this is the key point here. So by actually extending the second order to the third order, we are able to generate a circuit which is much less sensitive to variation in the input voltage. And for those of you who actually look at it as a current source, you can immediately appreciate that because this is a current source, the variation in voltage becomes less influential. So similarly, for the PP, we are able to extend it to this LCP circuit, with a voltage source behind an inductor, similar to the previous case. And we are also able to generate analytical formula or analytical equation for the input impedance, and we can also prove that it is actually much less sensitive to input voltage variation under certain conditions. So in summary, this kind of extension has an advantage of widening the input variation range. So in other words, the circuit will be able to cater for a much wider range of input variation. For the low side, we can apply basically similar technique, extending the LIC to LIV. Now, if it is a current, we are able to replace, or extend it to a voltage by adding, for example, here a capacitor here. So again, this is a second order to third order extension, and the voltage gain becomes, well, we are able to actually generate exact transfer function for the voltage gain, and we'll be able to see that the original LIC circuit will then be transformed to an LIV circuit, and under certain conditions, of course. So low side extension could actually be applied also to generate LIC circuit from LIV circuit, similar to what we provided earlier. So this is again a second order to third order extension by extending the low side, and fundamentally we are basically exchanging LIV condition with LIC condition. And in this particular case, from SP circuit extended to SPS circuit, we are able to show that the original LIV circuit is now being transformed to LIC under certain conditions. So in order to assess whether the system has an improved performance, for example, against input variation, input voltage variation, and also to maintain LIC and LIV still at the optimal efficiency point. And our tool here is the sensitivity analysis. So the idea is to compute the variation of, for example, the output voltage with respect to variation of a particular parameter. And for example, X is the input voltage, then we are actually trying to assess the sensitivity of the variation in the output against variation of the input voltage. And for comparing between two different topologies, for example, we would like to compare the third order circuit with the second order circuit after extending, from the second order circuit. We would like to compare, the change or the difference in the sensitivity. So the lambda here is defined as the relative, the comparison of the two sensitivities between topology A and topology B. So by doing this, we are able to understand whether there are benefits, or what exactly or what kind of benefits we can achieve by extending the second order circuit to third order circuit. For example, here we have the input voltage termination extending for the purpose of improving sensitivity against input variation. So by doing this, and we can show that in fact this lambda is less than 1, and therefore the LCP, so we are comparing the LCP with the SP circuit, and here because this lambda is less than 1, then LCP performs much better than SP circuit. Now, we are also able to identify the specific conditions for LIV. So remember, originally this circuit is designed for LIC for optimal efficiency, but by extending the output terminal to LIV, we are actually able to preserve the same optimal efficiency point where LIV condition can also be achieved. So this is the key advantage of expanding the low side. Using the same sensitivity analysis, we are also able to compare the sensitivity of different topologies against other parameters such as the primary inductance, the secondary capacitor, and the coupling coefficient. So similarly, we are using exactly the same technique, but just comparing different parameters. And for the case of LP, we actually found that the LCS topology performs better than SS topology by extending the input side here. Okay, so because the sensitivity, this relative sensitivity is less than 1. In fact, we have actually done a complete analysis looking at all different types of parameters and how the circuit, how sensitive is the circuit against variation of these parameters. And here's a comparison table for different topologies, including the SS, LCS, so that is the extension at the input side, SPS, an extension at the input side as well, and also the extension at the low side. You can see that some obvious advantage can be observed. For example, a much wider coupling range can be obtained with the SSP circuit. So through simulation, we are able to see exactly the same effects. In fact, by comparing the sensitivity of different topologies. For example, in this particular case, we are comparing the sensitivity of the transconductance against the values of the variation of the primary inductor, and we'll see that the SSP circuit is a lot less sensitive. And similarly for other circuit or for other comparison, we'll see in general the higher order circuit actually has far less or far lower sensitivity in general. Okay, and experimental circuit also confirm the same understanding, that is the higher order circuit under appropriate choice of parameter range are able to produce circuits with much less sensitive performance against, for example, input voltage and variation in coupling coefficient and variation in some of the inductances or leakage inductances and so on. So in summary, we are able to produce some very general design pathways for connecting second order compensation with higher order compensation. So we start with, for example, SS compensation and SB compensation for input voltage termination, and input extension is actually possible, transforming the PS and PP compensation to LCS and LCP compensation. And for the low side extension, LIV and LIC conversions will be able to maintain a higher tolerance to fluctuation of the compensation component, CS for example. And in particular, the SS topology can achieve LIC with optimal low sensitivity to CS fluctuation. And therefore, if we would like to preserve this very simple and useful advantage, and at the same time to serve LIV application instead of LIC application, then the low side transformation becomes very effective, and we can then extend the secondary side to SSP to achieve LIV, because originally it was LIC, but then it could be transferred or converted to LIV and preserving the same advantage of near zero sensitivity to CS variation. And finally, for both the input side extension and low side extension, we are able to widen the coupling range and therefore to provide a higher degree of freedom for choosing parameter values. In particular, the output side extensions will perform much better with loosely coupled transformers. This means that in situations where high capacity is needed to address varying misalignment and transfer gap, the output side extension topology will be very useful. So in conclusion, this presentation provides a very simple and convenient view of the benefits of higher order compensation. First of all, by expanding the input side via voltage current source interchange, and also extending the low side or the output side also by exchanging the voltage and current. Of course, the use of sensitivity analysis will be very useful, comparing and confirming the advantages of extension to third order circuit. And the results and the idea presented in this presentation is actually published in a paper published in the IEEE Transactions on Power Electronics in the coming September. So with that, I would like to thank you for your attention, and I'll be happy to take questions. Thank you very much.